Cross compilation is quite hard. If you try to compile the Qt for a target hardware like a Raspberry Pi specific hardware, you can have multiple problems. If you see in my previous tutorials, people are commented about the problems, these kind of problems. Probably they follow different steps, and each step create multiple, the possibilities to have different problems. So in this content, in this video content, I will show you a different approach for this compilation, and we will follow, all of us follow the same rules. So simply we will isolate the build environment. So we did actually before, like with virtual machine, but now we will use Docker. Docker is kind of an isolation. It isolates the environment, whatever you have. Right now, of course, we create some images, and we will use these images for build process. But Docker mostly, as I see, it is used for microservices management and for the web development stuff. But we can use Docker for our compilation environment, so we can isolate our environment. So in this content, also you will see that we don't need to have Raspberry Pi itself. So let me recap what we did before. If we want to compile the Qt, first we need a sysroot, right? So sysroot is a root of the system. You need to show to Qt where is the libraries, related necessary dependencies like headers, libraries. So all of them are in the sysroot file. Before, we just update the Raspberry Pi itself on the hardware, the real hardware, and take all these directories to the virtual machine, our build environment, to show the path, in the cross tool chain or during the command line, as a parameter, because it's necessary for the Qt. Qt should know where are the libraries, because when you run the application on the Raspberry Pi, it will check these libraries, right? If it is needed. And also you need a toolchain. Everything starts with the toolchain, not only for the cross compilation. Toolchain is important. We can do these things. We can update the Raspberry Pi. We can emulate the Raspberry Pi, Raspbian operating system actually, on the Docker, with the Docker. And we can simply build all toolchain and create Ubuntu build environment and compile the Qt in a Docker, which will give you ability to run this all the commands in an isolated environment. That means if you see a problem, I will see the same problem as well. So this will, decrease the problems, and we will all of us use the same environment, and the whole process will be less painful, I hope, as I see. But this is quite a magic. As I told you, I'm not kidding. We will not have the Raspberry Pi itself now. I will not show you Raspberry Pi during the build process. We don't need a Raspberry Pi right now. You don't need to turn on it. It is perfectly fine. So what we will do first, we need to install the Docker, that I'm going to show you the steps to install it. And later, using the Docker, we will create the Raspbian emulation first. Of course, we need to QEMU also for emulation. Then with the Docker file, that there will be two scripts, one for the Raspbian OS, the one for Ubuntu. And using these scripts, we'll create images. And at the end, this can take some couple of hours, according, it depends on your hardware, of course. I tried this to run all the steps in a 16 GB RAM on a Linux, and it took around 6 hours. It can vary, of course. But don't run this on the virtual machine. It will be slow. It will take 12 hours, or it depends, of course, still the RAM amount, but of course it will be slow. So as long as you run the Docker, this is important. As long as you are able to run the Docker on your system, you can compile the Qt on Windows as well. It doesn't matter. Operating system does not matter anymore. As long as you run the Docker engine, that means you are able to compile the Qt without having Raspberry Pi. This is good. So I have an Ubuntu machine here. I use, it doesn't matter, of course, as long as I told you, as long as you're able to run the Docker engine, it is perfectly fine. Now we install the Docker. Of course, we need to update our system first. There are a few dependencies for Docker. As I told you, you don't need to try this this approach on a Linux. You can try these things on Windows as well. You need to update a stable, this repository for the Docker. Otherwise, it will not be, it's not possible to find it. So now we can install the actually, first we need to update it. We need to update the system. Now we can install Docker. After this, we will run a Hello World application for Docker. That if you see this Hello World, it's working, then Docker is installed perfectly. Everything is all right. Just run Hello World. So there is no local image for us right now. So it will, it will be pulled from the repository. So there is a hello from Docker. That means so now you install the Docker. It's perfectly fine. You need to give some, the permissions for your user. Otherwise, you can run all Docker commands with the sudo. But let's give some enough permission. It's up to you, of course. This all steps, everything is available in my GitHub repo. You can find all the links below the video. Now we are now we are going to install the QEMU. So QEMU is needed for emulation. We are going to emulate Raspbian operating system in the Linux, in our Ubuntu system. The Raspberry Pi is, because it has different architecture. It is ARM, but our computer is Intel. Is x86, right? So now this command makes actually this is a kind of a settings. After this, you will be able to run the Docker with the QEMU abilities. So that means you will be isolate the QEMU also. This is good. There's a JSON file. You need to update this JSON file as well. I tried it without updating it. Everything worked, but I just followed what's the best practice. So just create a config JSON file under the Docker and put there experimental enabled option. So it's an experimental thing, quite. So now it's you need to restart the Docker. It's okay. There is no problem. Now Docker is working. Let's clone the repository first. Then I'm going to explain the Docker file, the content itself. There are two Docker files. In the beginning of this process, of this experiment, I was thinking to create only one single Docker file, but it didn't work out. I want to easily change the stages between different architectures, but it didn't work out. So I saw some different problems, different weird behaviors. So then I end up at the conclusion that I need to split the Docker files. So to run this, first we need to run, the Raspbian image, Raspbian Docker file. So I created here the Docker file rasp. To run this as the QEMU with the emulation, you need to use the buildx command, which means this QEMU. So you need to run this the command. The rasp image is the name of the image. As you see that it is now running. So, but what is running behind? Let me show you. If you check the Docker file rasp content, you will see some kind of some bunch of commands. Actually, they are Linux commands that we run before. So if you see, this is from means you defining the operating system, the architecture, right? I'm using ARM64. So this is important. Raspberry Pi also you can run 32-bit operating system. But in this case, you should use the correct image for your Raspberry Pi. I choose 64, ARM64, because I know I have 64-bit operating system. And my image, I mean, I choose the image as a 64 operating bit system, you know. If this is important, if you choose here 32-bit, then you will see later you will see problems. So which will be hard to handle. Be careful. This comment, this line creates, this says that the Docker file says that, hey Docker, create the Linux, Debian, and ARM64. But be careful, we are now running on the Intel, x86, right? So we have different architecture on the host system now. But we are able to emulate the Raspbian with Docker. This, the next one, the environment variable, it says there will be no interaction. It's just a command line, run as a command line. You don't need this, but it is okay to have it. This is just a created log file. If in case of any problem, you know, you can check this. You can copy this log file to the outside of the image, outside of the container, and you can, if you have a problem, you can debug it. So simply here, as you see, there are some repositories that we need to edit. These exist exactly in my Raspberry Pi. I checked it before. Then the other parts are simply as you checked my previous tutorials, they are the same packages. After this all lib, usr include, usr lib directories are zipped to the rasp-tar.js file. Later on, when this process will end, you will copy this file, this tar file, with the same place, same location where this Docker file exists. This Docker file is the longest one here. As I told you, right? There are two Docker files. So this tar file, this rasp-tar.js file, will be used here. See, it will be copied to this image, which is created by this Docker file. So then later, this will be on tar to the sysroot, under the sysroot file. And this sysroot file will be used in the toolchain here. Where is it? It should be somewhere here. See? And this toolchain file will be copied somewhere here under the build directory that I created, but I'm going to explain it now more. After this, you will have the actually the Qt binaries at the end, but let's come there again. So let's back to our Raspbian image, right? So as you see, this is running. It will take a couple of hours. Now, as you see, that it is like a normal Linux, but it is ARM right now. It is emulation. So the point is here, you don't need a Raspberry Pi anymore. So what we did before, we copied all the sysroot from the hardware itself. But now we are on the same host environment, and we are able to create this the all sysroot on a single host build system, let's say, with the Docker isolation, of course. So after it finishes, you can check that with the Docker images. You have a Rasp image. Of course, we run this before, the hello world and the other one. Now we have a Rasp image. As you see, this is quite more than 2 GB. Then simply we need to create a temporary container for it. Otherwise, it's not allowed to copy it to the outside. So just give temp arm. You can delete later, but I will leave it as it is now. It will give you some warning. Don't worry, because it says you created the container for ARM, but you are using the Intel, the x86. So what's happening? So just simply copy the tar file under the build from this container to the current location with the same name. Now we have this tar file. In this tar file, if you open it, don't open it, it's quite, it's 2 GB. You will see that necessary headers, libraries, but this is not necessary. This is not enough actually. That I will show you next, that some the binaries for the sysroot, for example, under the OPT directory, if you remember the previous tutorials, if you check it, there are OpenGL libraries. So we will download these libraries from the repository itself later. This is the trick. So now we are going to create the build process for the Qt and the image, I mean, with the Ubuntu. So, but just as you see here in the command, we didn't give the path or the name of the Docker file itself, because if I use the default name for the Docker file. If you give the Docker file name is a Docker file, you don't need to show it in the command. So it is running now, but let's check together first again. What's the content of this Docker file. So if you remember in the Docker file, in the Docker file RAS, there was a from platform Linux ARM, and it shows that this is for Linux ARM 64 and it's a Debian. It's the same in a Docker file, which is for Ubuntu. We will have quite same Ubuntu 22. I gave Ubuntu environment as a name that I don't need for this, but you can have it. It's okay. And again, non-interactive. It's just it will act like a command line. Then for each run, in this run commands, as you see, also these exist, or this is here, right? You can run the Linux commands, right? This is the point. So I update the Ubuntu with the necessary dependencies here, because these are actually these most of them are needed to compile the toolchain itself. So in this tutorial also you will see how to compile the toolchain. There is a build log here, like the previous one. If you have a problem, you can check the log. This workday build, is simply I create a build directory. When each run this command run, it will start from this build directory. Okay, it doesn't matter. Even if, for example, I make some cd to / whatever, some path, it doesn't matter. When I run again the commands here, it will start from the build. So be careful about it. I create some directories, necessary directories also. Then this is first, of course, before the Qt compilation, we need toolchain. So we will install the related files to compile the toolchain. So we need binutils, glibc, and gcc. This is for the firmware, actually the kernel. So let's talk a little bit. It's all right, but I will give more details. You can find in the link below the video. I don't want to explain every details in this video, but the binutils for binutils for the necessary. This is binutils. Binutils is a collection of binary tools used to manage the binary object files, libraries. So this is necessary. And glibc. This is a standard C library. Most Linux distributions, it provides the system call wrappers and basic functions for memory allocation. So this is also necessary. And GCC, this is a compiler collection. So if you have a program or you want to create a program, you need to have GCC. So you need 3 of them. And of course, the Linux itself. This is for also, it is needed later actually for the libraries. I extracted tar files and some under OPT to show there's a cross GCC directory. You can change the names if you like. I gave the path also to set the path to use it later. So this part compiles the toolchain, these lines. I take the reference from this this link that you can check. There's a script. They follow the same manner, quite exactly same actually. I just copy paste from there. So you need to. There are a few cases a few points that you need to be be careful. So you should choose the correct kernel version, which is 8 now, because I use a 64-bit operating system. And you need to define the architecture as ARM 64, like here, right? Remember, like here. This should be same for all the parts. Otherwise, it will fail. And you need to give some paths. this commands, the first we need to build the binutils and give the target as an arc64, see, with the ARM v8. Then after this, there are some small details that you need to update some files. I just found on the internet. Then you simply compile the glibc partly because it's needed later. Then you need to compile GCC partly again, and you will build again the glibc to complete it, and you will complete the GCC compilation. After this, you will have complete, ready-to-use toolchain for Raspberry Pi. You can run also these commands, if you like, with your hand to see what is the point. After this, as I told you, we need a sysroot, right? So you create a sysroot directories. This is the next steps, and you copy the tar file here. I mean, it will copy the Rasp target.js that we created here to the under the build directory, and also it will be untar under build sysroot. So this, as I told you, this sysroot will be in the toolchain file later here. This is important, and is in the toolchain file. You need to also define the architecture correctly, and you need to give the path for the the compiler for the CMake correct target. Or as you see that these directories that I created that I'll show you, cross P, GCC, and also you need to correctly show the related SO files for the windowing system, like an OpenGL, as you see, and a libgl. These are not coming from the image that we created before. This will come from the repository itself. So because in the emulation, you cannot emulate hardware directly. That's the point. That is why it's called emulation. That's why it's called emulation, right? Otherwise, it will be something else, directly the simulation or something. I mean, you can emulate the software, but you cannot emulate the hardware. But we need hardware-dependent libraries. We need hardware-dependent drivers, like an OpenGL, AGL drivers, right? To tell to the Qt, we will use these libraries and bind it. To do that, you need to install the firmware. You need to clone the firmware. To do that, you need to clone the firmware of Raspberry Pi. If you check inside, there is if you see that there is SO files, then you can download these SO files directly to the image here. And I just, instead of download the one by one, I just copy all the OPT directory under the sysroot OPT. So now we will have the complete sysroot with the related OpenGL libraries also. This is good. Then we need to copy the toolchain under the image, under the build directory into the image. Also, we need to build the CMake itself. That I saw some problem that the version was quite old and I want to compile the latest one. Then I compile the CMake here. Then now this part is the real part of the Qt compilation. Here just this for fix the symbolic link that if you remember in my previous videos, when you copy the sysroot from some place to another place, you need to fix the symbolic links. And just create some directories that you can change these names, it is okay. This is for host compilation for the Qt. This is for Pi compilation, the cross compilation. So just install, just get the tar files. As you see that this image will compile Qt base and Qt QML simply. I mean base and QML. So if you want to compile the other parts, you need to put here. I didn't try all of them. There can be problems. I will check it. Probably I will update this file. It's quite, it looks quite messy a little bit, the file. Because I intentionally do this. I think it is easy to understand in this way. But probably later I will update it. Then just untar these files for the host compilation. Compile Qt base for host. Compile shader for host, compile declarative for host. After this, untar them again. You can untar this for just once, but I did twice here. It's okay. It's not a big thing. And compile the Qt base for Rasp. These lines, these parts, compile the Qt for Raspberry Pi. This is the CMake and the related options that I choose. OpenGL ES2. Some this is test of this normal options. You need to give the prefix correctly. See that we created before. This is important because this part will be tar later. So you can copy this tar file, this content of this directory, and you can send to the Raspberry Pi. Later we will test it. And target device, as you see, this is just I just copy paste from my previous tutorials, as I remember. And xlib on that. You can also change these things to test, to experiment. It's perfectly fine. After this, if everything goes well, you will have 3 tar files. First time, this Cross Pi GCC, this which is a toolchain under OPT for under build, sorry, and the host binaries and the Pi binaries. If you want to create a development environment like that we did before, like a traditional way, you need these 3 tar files. You need to extract them. You need to copy from the image, and you need to extract them. That's why I did like this. But normally, we will need only this one right now. And this will create just a project file. There is a project directory. So this will be copied to the under build project, and there's a hello world application. If everything goes well, as I said again, it will compile the hello world application. Then we will copy the binary directly from the container, and we will see that. We'll try to run it on the Raspberry Pi, that you will see the magic. So then let's go back. Let's see what will happen. That, as you remember, we just try to create the Qt Cross build image. This will take a couple of hours. So you can leave it as it is. You can leave it like this and do your job, continue your life. If you check correctly, each commands, the blue ones also here. This shows the run commands that I showed you, in the Docker file. So if you see if one of them, just fails, then probably the whole step, the image creation will stop. It should stop. This is the good part actually that I will show you. After some time, of course, I just stopped the video here, but after some time, you will have like this. That means the image is created correctly. Everything is all right. And then you need to create a temporary container that you did before to copy this tar file and the binary file. As you see that with the Docker images, now we have Qt Cross build image, which is a 31 gigabyte. This is quite huge. So this is one of the trade-off actually. It will take, but it's not like a virtual machine, so it's still doable. It's still okay. 30 gigabyte for the Qt the portable build, isolated portable build environment. 30 gigabyte is good. I don't see a problem. So let's create a temporary container for this image, for Ubuntu image, which has our tar file for Raspberry Pi, the Qt binaries, pre-compiled Qt binaries, and our the Hello World application. I gave them a temp build. You can give whatever you like, but don't forget to delete it. I don't do that now. So simply, you can also check with the Docker ps -a that it will list the containers. So now we have temp build container. Well, we can copy simply the tar file, which is under the build, and our Hello World application. Qt Pi binaries tar, and with the same way. Of course, we need to copy the example, the binary which is compiled already, the Hello World application. So it's cool. With a single Docker file, you will have everything. This is quite handy. And it's more portable. You can do that You can do this on Windows as well, or wherever you like. Wherever you like, you will have this tar file. You will have the precompiled Qt binaries for the target hardware. It's quite nice. It's quite advanced method actually. It's good. And let's copy the the binary, which is under the project directory in the image, in the container, not an image, container. So the name is Hello Qt6. That you can change the name. I mean, it is in the CMake file. If you update the CMake file, the name will be different. But you can quickly also check this the binary with the file command, the content of. You can have a knowledge about. You can have an idea about this Hello Qt6 binary. If you check with the file, you will see that this is compiled for ARM. So it has succeeded now. It's good. The next step, let's try this. Let's test this hello world and our binaries, our precompiled binaries in the real hardware, in the Raspberry Pi. Be sure that you are able to ping your Raspberry Pi. As you see that I don't show you any Raspberry Pi right now, right? So we have Qt Pi binaries, tar file and hello Qt6 binary. So simply send this to your Raspberry Pi with the CCP or whatever you have, the FTP or whatever, which protocol which one is your best. I don't know which one you will prefer. Just send them somewhere under the desktop or somewhere, This is my Raspberry Pi name and IP address. I need to type it correctly. SSH. Using SSH, you can connect, the Raspberry Pi. As you see that we have here the Hello Qt6 and our tar file. To use this, you need to untar this tar file somewhere under USR local, because our Qt application will use these binaries. And untar it under the USR local. Later, of course, with the sudo. Later, we will. You need to export this. Don't forget to export the path, the LD library path. It is here, as you see. If you check with the ls command, all the necessary directories and binaries are here. As I told you, you need to export the path before running the binary. Otherwise, the binary will give an error and it says, I cannot find these libraries. I cannot find these so files. USR local Qt6 lib. Now it is time to run application and data. It's a magic, man. It's something else. We didn't touch even hardware. Of course, before running this, I update the hardware. I run the RPI update and RPI update, upgrade, whatever the other things to update the Raspberry Pi. But it's not about it. So I didn't touch the hardware in the beginning to create, to build the Raspberry, to build the Qt, to compile, cross-compile the Qt. And at the end, I have these libraries, pre-compiled libraries, cross-compiled libraries for the Qt, and I have an application, and I just send them to Raspberry Pi, and everything worked. It's a magic for me. Now let's assume that, for example, we want to change the project. Right? It's a quite simple project, and let's create the window with the QML. Let's test the QML. I'm going to there are two directories, project and project QML. If you change the project QML, or you can change also Docker file, but I will move here the project QML as a project. So I just first move the project directory as a project 2 or something. Then I'm going to change the project QML directory name as a project. So now the Docker file, or actually Docker, will see that the content of this the project is changed. So now then it will run the related steps when you run the build again for the Qt Rasp image, for Qt cross build the image. But be careful. If you change any commands in the Docker file, the previous commands, Docker will understand there's a change and it will run again everything. So don't do that, be careful. Also, you can create the stages to run the specific part. So if you don't touch any commands, the previous commands in the Docker file, the Docker will cache, actually the Docker cached before the previous command, so it will not run again. So what we will do now, simply, if you check with the images, I mean, what was the name, Qt cross build image. Now we will run the Docker build command again. And you will see that only the necessary part, which is related to this project compilation, will be run. This is the beauty also. So you don't need to run again. So you can compile your application in the isolation, in the Docker isolation. It's perfectly cool. Wherever you have this image, if you have this image, I mean, wherever you have it, will be the build environment for the Qt, for development environment. This is cool. So as you see that, this is all cached. That means it will not run again. So just the only part which is running now, the project itself, that we change the content of the directory. And it will create the Docker, the Qt hello QML binary name or something, I don't remember, let's check. Why this window is bigger now? And simply create a temporary container again. You know, we created before the container, but it was, you know, there is no our new binary, so you need to create a container again after each run. Temp with QML, that I just gave the name, that it's up to you again. And the container now is created, temporary one again, as I told you, but delete it. You can delete these things. And copy this binary from this temp with QML container. It is under project directory, somewhere here. It doesn't matter, we will send this to the Raspberry Pi. You can check with the file commands again. It will, as you said, it's compiled for ARM. That's cool. And let's send this to the Raspberry Pi. Of course, I also forget that you need to copy the QML file. I didn't embed this QML file to binary, but you can do that as well. But you need to also just copy the QML file and send to the Raspberry Pi. So hello Qt 6 QML and main QML should be sent to the Raspberry Pi like before. Home, it's a name, it's my name. I like to give my name to the embedded boards. Then I'm going to show you the different the way to run this example. Still, I don't show you. See, as you see that I don't show the real hardware still. I mean, this is running on my table, but you don't need to see it. This is cool. So now we have hello Qt QML. If you try to run it, it will give you a problem because we didn't export the the display. So it's perfectly fine. We expect that. But I'm going to show you another trick now. Without touching the screen of the hardware, without looking to the real hardware screen, how we can run this QML application, which is on the top of the X server, with the SSH. So use the -X argument, the capital X. Connect SSH with the capital X to Raspberry Pi. This will redirect the X server output, the X server, the all windowing, the coordinates, everything to your host here, to your host system. If you export again LD library path, then if you run the QML application, you will see that the window will appear on your system, on your host. It's cool. And you can interact with it also. You can click the button and you will see that it will be clicked. As you see, it is on Raspberry Pi. That's cool. So that is all for me here. In this content, you understand the basic concept of compilation the Qt with the Docker isolation and seeing the advantages of it. Of course, nothing is perfect and nothing is free. So the debugging is really hard. If you have a problem, because it's an isolated environment, if you have a issue during the compilation, It is so hard to understand. You need to read the log file, or you need to maybe log into the the container, the build container itself. It will be really hard. So before changing the Docker file itself, if you know what you are doing, it's okay. But if you don't know the result or any steps, I recommend you to check the steps first in the virtual machine. Then copy the steps easily to the Docker file. You will have probably the same result as an output. So that is all for me here. If you have any problems, you can leave a comment. And as I told you, all the steps, all this theory and the more details are in the, there are links below the video. And one of them is in my GitHub and in the website. You can find more information. In the second part, probably I'm going to create another tutorial about to use this build environment now, with the interactive development environment with the connection with it. How we can do that, how we can use it. Right now, I mean, I just copy paste the project file, but what if we want to use Qt Creator or the VS Code? How we can do that? What are the possible ways? We will discuss these things. Thanks.